So this recording is going to go through the basics of probability. Um, the objective here is you're going to be able to use some of the basic terminology associated with probability, and you're going to be able to use or to calculate probabilities using some of the basic properties, the multiplication, addition, and complement properties of probability. So we're going to start here. A random event everybody kind of knows is flipping a coin. Well, instead of if we don't have a coin handy, we can actually use our calculator to randomly generate some numbers to pretend we're flipping a coin. So in other words, we got heads or tails. Well, what we need is we need these random numbers assigned to the events. So for us, we could use a digit 0 to 9 and just randomly start coming up with these integers, but we need to split it 50-50. So maybe we could say if we get anything from 0 to 4, that's like flipping heads. Anything 5 to 9 is like flipping tails. You know, uh, maybe anything evens would be heads, anything odds would be tails. That would split it 50-50. Um, Again, what you're after there, we'd be using the random integer function, and then uh, we would want to make sure that we tell the calculator we want something from, 1 or 0 to 9, so it doesn't pick anything that we don't need. Now, another option, so we don't have to do too much thinking, we could also just use the digits 1 and 2. Let me erase what I just wrote there. Um, uh, and where 1 is heads and 2 is tails. So instead of 0 and 9, now all of a sudden we could um, just use 1 and 2. So maybe using 1 and 2, so we just generate a random number, random integer 1 comma 2, and it'll just, that's basically like flipping a coin back and forth. Um, so we just want to try to figure out how many trials we want to do. So maybe we think, all right, let's do 3 trials and then go ahead and execute the simulation. So let's say that we actually did this thing where we went ahead and we did random integer 1, 2, between 1 and 2. So random integer, I'm not going to type all that in, but we know where that function is. It's in the math probability. And if we're going to do 3 trials, why don't we just go ahead and put 3 in here, and then we're going to let the calculator go ahead and run it. So let's say that we get, tails, heads, and then a tails, right? So that would be like if our calculator kicked back 2, 1, 2. So we got tails, heads, tails. Well, the probability we got a heads in this simulation was 1 out of 3, and the probability of tails is 2 out of 3. All right, so trial 2, let's say that we ran the same simulation again. This time we got heads, heads, tails. All right, so let's say we got 1, 1, 2. Well, now the probabilities of heads and tails in this particular event have changed just a little bit. So now heads 2 out of 3, tails 1 out of 3. And let's say we did it one more time, and all of a sudden it kicked back, 2, 2, 2. So all of a sudden we got tails, tails, tails. So now all of a sudden the probability of heads is 0, and the probability of tails is 3 out of 3. Um, and so if we started to kind of try to combine these things, what we'd start to see, so we got 9 total trials. In the long run, we should start to see something kind of play out. So this is 3 out of 9, and then this would be 6 out of the 9 flips, or tails. Um, but what we're looking at here in each one of these examples with these probabilities that are here, this probability heads, probability tails, this is a probability resulting from an observation. What's called empirical, or another E word which goes right with it, experimental probability, what we actually experimented to do. And what we need to realize is that in the short run, chance behavior like flipping a coin is random. However, the law of large numbers says that in the long run, the relative frequencies of repeated independent events settles down to the true probability. So let's say we wanted to run a huge simulation where we flipped a coin 200 times. Now this is where the calculator or some kind of random number generator is awesome, because then we don't just flip a coin, flip a coin, flip a coin, flip a coin. We can run them all very, very quickly. And here's a way you could do that in the calculator, where we go to list 1, we highlight L1, and then we can generate 200 flips in list 1. Once it's highlighted, just doing that random integer 1 comma 200, 2 comma 200, excuse me, and it'll generate 200 flips of the coin right there. Real easy way to count it. I suggest, instead of having to scroll through 200 ones and twos, just create a histogram with that data. The trick here is right here, setting up your x-axis. You want to go from 1 to 3, and 3 because your bin starts at 2 and ends at 3, and then your x scale will be 1. So that's basically going to put everything from 1 to 2 in one bin, everything greater than or equal to 1, and then less than 2, and then everything between 2 and 3, your 2's in the other bin. And you can count it very, very quickly using the trace function. And what we should see in the long run, we're going to start to approach this theoretical probability, uh, which should be 1/2. So if we flipped it 200 times, we shouldn't get anything all of a sudden 200 heads and 0 tails. We should get something closer and closer to about 100 of each. If we did it 1,000 times, 10,000 times, what we would see, the more trials we do, the closer we're going to get to this theoretical probability. So according to that law of large numbers, as the number of trials increase, the empirical probability is going to get, the empirical or the experimental, what we actually do, should get really, really close, if not right there. If we go to infinity, if we could flip a coin an infinite number of times, we would hit 50-50 exactly. So some of the terminology that you need to know. Trial, it's a random event, flipping a coin, rolling a die. The outcome is the value of that random event, and then sample space would be the set of all possible outcomes. So let's say we wanted to flip a coin 3 times. There's your random event. Your outcome, let's say we want 2 tails. So there's actually 3 ways to get 2 tails out of the entire sample space, which is all possible outcomes. So these are down here at the bottom. These are all the possible outcomes if you flip a coin 3 times. And then what we'd be interested in is the outcome of exactly 2 tails. And so there are 3 out of 8 possible ways to get exactly 2 out of 3. So the probability is always the probability of an outcome. And sample space will essentially be, when you count those all up, that's your denominator. So let's say that we want to roll 2 dice and record the sum of the numbers showing. The sample space for us, you can roll a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? If you play Monopoly, if you play any other game. But the question here, are all the events equally likely, right? Keep in mind, event or outcome, right? The value of a random event. So are all these outcomes equally likely? And the answer to that, if you start thinking about it, there's one way to get a 2. You roll a 1 and a 1. Well, for a 3, you could roll a 1 and a 2, or you could roll a 2 and a 1, right? Now all of a sudden, if you start thinking about this, there are 3 ways to roll a 4. A 5, you can do 1 and 4. 4 and 1, you could roll a 2, then a 3, or a 3, then a 2. So there's all these different outcomes, all the way down to 12. There's only one way to roll a 12, which is a 6 and a 6. So there are a total of 36 possible outcomes. So the probability that you roll a 2, there's one way out of the 36 to get a 2. So on and so forth, all the way through. And we can see the probability of rolling a 7 isn't the same, right? The probability here, rolling a 7, isn't the same as the probability of rolling a 5. It's more likely to roll a 7, right? So what we can see is the events are not equally as likely. And the number of male children, so the sample space, if they're going to have 3 kids, uh, what are the different things that they could have? They could have 0 boys, 1 boy, 2 boy, or all 3 boys. So again, are these equally likely? So let's say there's no boys. That means it's all girls, female, female, female. Well, how many ways are there to get 1 boy? Well, you could have a boy and then 2 girls. The boy could be the middle child, or the boy could be the youngest child. To have 2 boys, that basically is kind of the other way around. Now all of a sudden the 2 boys are the oldest, the boy is the oldest, and then you got a boy that's the youngest, and then you have the boys that are the 2 youngest. So here you can see this is the order of the children. First, second child, third child. And that's a different order than when the male is the middle child right there in 2. And this is kind of the same thing if you think about it in event where there's 2 boys, it's the same thing. It's just 1 girl instead of 1 boy. And then how many ways can you get exactly 3 boys? Well, that's easy. Boy, boy, boy. So how many total outcomes? There are 8 outcomes, which means there's a 1 out of 8 chance that you get all girls. 3 out of 8, 3 out of 8, and 1 out of 8, right? And if you think about this for just a moment, well, one, we can see the events aren't equally likely. And how likely is it that you have all 3 kids that are boys or all 3 kids that are girls? It happens. It definitely happens. And you probably know friends and have folks that you know that are, all boys or all girls. But typically, it's a lot more families have a few of each. So some of the properties to look at, the probability of any event is always between 0 and 1. You cannot have a probability over 1. If you add up everything in the sample space, the probability is 1. And then this is what's called the complement idea. And these two, you might see A with that superscript C, or you might just see A with a bar over the top. Those basically mean not A. So the probability of event occurring is 1 minus the probability it does not. That's what these two things are, the complement rule. So let's say that it's the probability of rolling a 2 is 1 minus the probability of not rolling a 2. The big thing here with the addition rule, I mentioned this earlier, is when you see the word or. and then the multiplication rule when you see the word and. So this idea of disjoint and independent we'll talk about in the days that come. But right now, the big idea, if you see the word or, you want to go ahead and think addition. If you see the word and, go ahead and start thinking multiplication. So quick example, in a standard bag, yellow and red make up 20% of the candies, and orange, blue, and green 10% each, just to keep it simple, and then everything else is brown. So if we think about this, the probability we get a brown, well, add up, so 20% yellow, 20% red, that's 40%, and then 10, 20, 30 more for orange, blue, and green, so that leaves 30% for brown. The probability of yellow or orange, there's the word or, so you're just going to add those up, 20 plus 10. Not green would be 1 minus the probability of green, so since green is 10%, we use the complement rule, 1 minus 0.10. And then the probability of stripe, there are none. And then let's say we pick 3 in a row. We pick one out, we put it back in. We're not thinking sanitary here, but probability of all brown. So here's the idea, brown and brown and brown. So since we see the word and, we're going to go ahead and multiply those together. And then how about the probability the third one is the only red? So in other words, not red and not red and then red. So the probability of not red would be 1 minus 0.20. So the probability of not red is 0.8 times 0.8 times 0.20. Right? So in 2001, M&M's decided to add another color, and so they surveyed people in nearly every country, and the winner ended up being purple. So in the U.S., 42% of those voted said purple, 37% teal, and 19% said pink. So let's list the sample space of choosing a color. So purple, teal, pink, those were the 3 colors. Look at the first 2 properties really quickly. Are all the probabilities between 0 and 1? Yes, so far. And then is the entire sample space 1? Well, 42% plus 37% plus 19% actually isn't 100%, which means that we needed to identify a new event. Down here at the bottom, you can see it sitting there the whole time, of none. So there's a 2%, the 2% of people just didn't make a claim. So in Japan, the percentages were 38%, 36%, and 16%. Again, that doesn't add up to 100, so we'll go ahead and I think that only adds up to 90. Yep. And so the probability of none is 10%. So let's say that we're looking at the Japanese survey. What's the probability they preferred pink or teal? So that should go ahead in your head. You should be thinking addition. So pink or teal. So pink plus teal would be 0.38 plus 0.36, 0.74. And then if we pick 2 respondents, what's the probability they both said purple? So purple and purple, right? If we can start thinking about the words that we're using, purple and purple, that'd be 0.16 times 0.16. And then if we pick 3 respondents, what's the probability that at least one preferred purple? So this is a big thing to realize. There's 2 ways to do this, the hard way. At least one purple could mean they do 1 purple or 2 purples. So there's the or all 3 were purples. Well, within 1 purple, 2 not purples, think about this. It could be purple, then not, then not. It could be you pick someone that didn't want purple, and then the purple person was in the middle, and then you got another no. And there's another option here. The first 2 people you could talk to didn't pick purple, and then the third person did pick purple. So there are 3 ways to get 1 purple. Either the first person picked it, or the second person, or the third person. Within 2 purple and 1 not purple, same kind of situation. It could have been purple, purple, not, or the first person was purple, the second person was not, the third person was purple, or the first person you talked to wasn't, and then you got 2 purples in a row. Now, for 3 purples, there's only one way to get 3 purples. All 3 people wanted purple. But the issue here is there's a lot of options to start considering, right? And if you think about this, since the probability of purple was 0.16, there's 1 P in each of these scenarios, and then 2 N's. Well, the probability of not purple is just 1 minus, which is 0.84. So the big thing here is this 3 times 0.16 times 0.84 times 0.84. It's just all 3 of those at the beginning. Same thing right here. 3 times 0.16, 0.16 times 0.84. Those are all these options. And then finally, the probability of 3 purples. There's only one way to get 3 purples. And so you could put all those together, 0.407. Or there's a much easier way using the complement rule. And here's the idea. The probability of at least one purple would be the same. The opposite of at least one would be no purples. And so using the complement rule, we can do 1 minus the probability of none. So in other words, 1 minus no purple, no purple, no purple, which is where that 0.84, 0.84, 0.84 comes from. And that would be 0.407. So the complement rule, when you see this term at least one, go ahead and start thinking about the complement rule, 1 minus the probability of none.